All right, guys, welcome to this page of the notes. We're going to go ahead and do another example problem because I gave you a ton of information on the previous page of the notes, and the more times we do it, the more comfortable you'll get with it. So I'm going to do everything I did on the last page. We're going to do all of that for this problem as well. Please keep in mind that I don't ask you for all of this stuff, but at some point I will. And so it just helps. The more times we see it, the better at it we're going to get. So let's go ahead and do what I am asking you to do, which is to graph the logarithmic function. You're going to need at least 3 coordinate points to plot. So we're going to do f of x, x and y. We're going to go ahead and set up our table. Remember, I need at least 3 points to plot. So for my logarithmic function, those 3 points are going to be based on the base of my logarithm, all right? Now, there are no transformations going on here, so I know my logarithm has to go through the point 1, 0, and we'll get to that in a second. Now, based on my base, the base of this logarithm, which is 1/3, we said the inverse is going to be one of the x values you want to use. Well, the inverse of 1/3 is 3. So the first value I want to put in here is going to be a 3. And if you do log 1/3 of 3, you're going to get a -1. Go ahead and use your calculator if you need to. You shouldn't have to. I showed you here on this last page of the notes, whenever you do the inverse of the base, you're going to get a -1. Same thing here. I do the inverse of the base I've been given, I'm going to get a -1. You're also always going to want to plug in an x value of 1 because the log, it doesn't matter what the base is. Log any base of 1 is going to be 0. And again, feel free to do that as many times as in your calculator as you need to satisfy yourself. I'm not lying to you. I'm telling you the truth. Log any base of 1, you're going to get 0. And there's that point I told you would always show up as long as there are no transformations. We're going to go through the point 1, 0. And then the other one, right, is to whatever the base is, plug that in as a domain value. Since my base is 1/3, I'm going to plug in a 1/3, and when the base and the augment are the same, right, I'm taking a log base 1/3 of 1/3, the base and the augment will cancel each other out, and you'll be left with just a 1. We're going to go ahead and plot these points to get a picture of what my logarithmic function looks like. Remember, the y-axis is going to be a vertical asymptote. I go through the point 1, 0. Then I have the point 3, -1. 1, 2, 3, -1. And I have the point 1/3, which is 0.333 repeating. Careful, +1. Don't let this throw you off, right? It's not that big a deal, right? I've got a base of 1/3. You'll see why it'll make perfect sense to you in a second as I go through this problem. But I'm at 0.3, +1. So 0.3 +1 is going to put me somewhere right about there. The y-axis is my vertical asymptote. I got to draw a smooth curve through those points, and so it should look, hopefully, you get something that looks kind of like that. Make sure you extend your line all the way through the coordinate plane, and you put arrows on both ends so I know you know that graph just keeps going. And you say, hold up a second, what the heck are you doing? That looks nothing like the graph we did on this page where it was going the opposite direction, right? This one started at -infinity and came up. This one is now starting at +infinity and coming down. Why? Well, it makes perfect sense if you consider the inverse function, right? Remember, on this one, the inverse function was y equals 5 to the x power, in which case the exponential increases from left to right. Guys, on this problem, the inverse is going to be y equals 1/3 to the x power. And I made a huge deal of this in chapter 7, section 1. Whenever the base is a fraction, your function is going to decrease from left to right. So because my exponential looks different, it would make sense that this logarithm is also going to look different. They should still be mirror images of each other, however, when I graph them. So let's go ahead and do that. This is going to be my inverse function. So instead of calling it y, let me call it f inverse. And let's graph this one as well. Here we go. So f inverse of x. Remember, this is really easy to do. Inverse functions, the domain and range value switch places. So instead of 3, -1, I'll have -1, 3. Instead of 1, 0, I'll have 0, 1. And instead of 1/3 and 1, I will have 1 and 1/3. I'll go ahead and graph these points in red. It'll represent my exponential function. -1, 3, 0, 1, and 1, 1/3. Remember, for exponential functions without transformations, it'll always go through the point 0, 1, which I do, and the x-axis will always be your horizontal asymptote. It's the line that you approach. It's the line that you approach but never cross. Go ahead and connect my exponential function coordinate points with a smooth curve. Put an arrow on both ends, extend the line all the way through the coordinate plane, as I've done so that I know you know that guy just keeps going, and here we go. They should be inverse functions, which means they should be mirror images of each other across the identity function, which is the line y equals x. And if you take a look at that guy, you'll quickly see, or should be able to pretty quickly see that yes, the red and green lines are mirror images of each other across that line. And the reason they look different is because there's a difference between the base being a number greater than 1 and the base being a number less than 1. All right, so it'll make sense then too for logarithmic functions when the base is a number greater than 1 and when the base is a number less than 1, or a fraction. It'll change the way the graph of the logarithmic function looks like. So again, they are inverse functions. I graph both inverse functions, something you should be able to do or get comfortable doing. I will ask you to do it. And let's go ahead and find our domain and range. All right, for my logarithmic function, the domain. Again, take a look at this. The logarithmic function is in green. The y-axis is my vertical asymptote, and I only have things that are bigger, right, going in the positive direction. So my domain is going to be all values of x that are strictly greater than 0. The range, please notice that it starts at positive infinity and just comes down and keeps going, but we're talking about, right, the range value, the y value. So that guy will just keep going to infinity, which means the range is all real. All real numbers. But that domain and range should also make sense based on what you know about exponential functions, because they're inverses. All exponential functions have a domain that's all real numbers. So the logarithm will be the opposite of that. The range will be all real numbers. And all exponential functions, this one in this case, has a domain where the y values are everything greater than 0, because the x-axis is my horizontal asymptote. Well, the logarithm, the inverse, will be the opposite, right? Now the y-axis is my vertical asymptote, and it'll be all values of x greater than 0, right? The domain and range values are going to switch places. All right, guys, that's 2 example problems now where we have looked at both graphing the logarithm and the exponential function, how they're inverses and how those inverses tie together. Hopefully at this point you feel a lot more comfortable with it. I do have several more example problems that we'll go through just to make sure you're comfortable with all this, because it's a lot of information, I know. Just keep practicing, you'll get good at it, but these inverse functions are real important. Go ahead and head on over to the next page of the notes. We'll start looking at transformations. I'll meet you guys there.